So this is our first talk by Xin Wei at IGES, right? Yeah. So he's going to talk about hash families. Yeah,
Okay.
please.
Thank you very much for coming today. And my title today is Separating Hash Families and a Solution for Set. Maybe different from what you see in the in the web, but it's just a problem of separating hash families, and I use solution-free set to solve this problem. And let's begin with the definition of perfect hash family. And this is a special type of separating hash family, and actually we will mainly work on this part. And a perfect hash family, it has such 4 parameters. I just pointed. The first 3 means it is a capital N, little n-q hash family. And the first one means it's satisfying what is called T separating property. For the first one, n-q hash family is just a family of functions, f1 to f capital N. It has n function, and each function it goes from the universe we call x to the alphabet we call y, and the universe has the size of little n, while the alphabet has the size of q. For an n-q hash family, we can present it in a matrix just like this one. So it is a capital N times little n matrix. For each row, it corresponds to some fi. And for each column, it corresponds to some element in the universe. So if we go for the ith row and the jth column, here, for this block, the value is fi xj. So it is part in the alphabet. So under this correspondence, n-q hash family is actually n times little n matrix over what we say f2, something like that. And then, what is the T separating property? For any given element x1 to xt in the universe, such that they are pairwise not equal to each other, then there exists one function such that the values of those elements are pairwise not equal. So in this language, how do we say about the T separating property? We put T columns, right? Because each element in X represents one column. Then we can always find one row such that those columns have a different values on this row. This is what we call T separating property. So is this clear for perfect hash family? Actually, we have an example. This matrix means here we have 6 rows and 12 columns. And the first 3 means all of its values are from F3, means only 0, 1, 2 are inside this matrix. And the second 3 means if you choose 3 columns, then there must be one row separate those 3 columns. For example, if we choose the first 3 columns, then the last row separates these 3 because 0, 1, and 2, they are mutually different, right? And if we choose the last 3 rows, maybe the last 3 columns, maybe the first row separates it. And SHF, it is different from PHF just in this kind of parameter. So it is still an n-q hash family, but not T separating property. but we say W1 to WT separating property. So what does the W1 to WT separating property means? For PHF, we choose T columns directly, but in SHF, we choose T pairwise disjoint subset of X, such that for each Ci, the size is Wi. Here, each Wi is a positive integer. Then, we want to say there exists one Fi, which means one row, such that rows things are pairwise disjoint. And we say Fi separates C1 to Ct.
So FICI is just a like vector or so Ci is a set, right? CI
Yes. So FICI is also a set, not a multi-set. For example, if we choose these three columns, we say these three columns, and we say let this two column to be C1 and the second column to be C2. Then this row separates C1 and C2 because the first FC1 is 2 and FC2 is 0. They are disjoint.
I see.
And the sum of WIs are always at most Q?
The sum of Wi, not always. When it
The Q is the size of Y, right? So nothing to do with.
Q,
Yeah, but Fi of C1 there. Okay, so Fi of C1 is not necessarily all distinct, but they
Yeah.
can have overlapping value.
yeah.
Okay.
Right. They are sets, right? FIC1 is a set.
Mm.
Mm.
So in this definition, this PHF equals to this SHF, which means we take three rows, or we take three columns, and also it is 2-1 SHF. Right. This is the definition of these two things.
So, sorry, do you mean this this PHF is equivalent to the 2-1 SHF, or it implies the 2-1 SHF?
It implies 2-1 SHF. These two are equivalent.
So do you really want pairwise disjoint, not distinct? The set has to be distinct? Disjoint?
Disjoint,
Non-empty intersection?
which means intersection is empty set. So SHF and PHF, they are important structure in many areas such like cryptography and coding theory, and actually is a generalization of many well-studied objects, such like the frame-proof code and parent identifying code. But I do not want to go too deep into those definitions. So you just need to know these things are very important. So why we want to consider these two things, SHF and PHF. So when given such n, little n, and W1 to WT. By the way, W1 to WT is always called the type, separating type of one SHF. And after we give big N, little n, and the types, big N, Q and the type. We always want the number of the columns to be as large as possible. So this goes to this definition. For sure, we say this is a C value. C value means the largest n such that n SHF exists. And if we go to the PHF, we just use PTNQ to be the short form of CNQ1, blah, 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 1. Here we have T times of 1. One observation of studying PHF is that PHF, we say, is the strongest SHF. How do we see this? If we fix the sum of all the WI, then if an SHF, it is 1, 1, 1, the sum of Wi. We always say this to be U separating. Then it must be W1 to Wt separating. In this sense, PHF is the strongest SHF, and we have PU and Q is the lower bound of this C value.
So the PHF means perfect hash family? Or?
Yes, perfect hash family,
Mhm.
and SHF means separating hash family. For separating hash family, the C values, we have this classical upper bound and lower bound. Here, what we want is when Q go to infinity. And as you can see, the only difference between the upper bound and the lower bound is only a scaling function in the order of Q. So, if we have U minus 1 can divide n, then this upper bound and the lower bound just give the right order. So what can we say if this does not happen? Blackburn raised a question, and he conjectured that the upper bound can be always be reached as near as possible, which means we can, for any arbitrary small epsilon, when Q is large enough, we can always find an SHF of the size of this one. And here, this is the order of the upper bound. The first breakthrough is that for PHF, when n equal to t and t equal to 3 and 4, this thing has been proven. And our main theorem is that not only t equal to 3 and 4, but for all t larger than 3, this statement is right. Hence, we can answer the question of Blackburn affirmatively for any n such that the order equal to 2. This is the order of the upper bound. From our main theorem to this corollary, just leave the observation that PHF is the strongest SHF. From this to this is very simple. What we are doing now is try to prove this main theorem.
So capital N is the number of functions in the
Yes.
family,
Yes.
and U is basically the order of the set that you want to separate.
What?
Like U is the sum
Yeah.
of WIs.
U is the sum of Wi. And here, for this, we want U to be N to be T. All these things are the same.
Okay, so for in that N equals 2, N equals T as well.
What?
So you wrote capital N equals T.
Capital N, yes, capital N equals to T. Because here we have N and U and T all the same, because T is W1 to Wt. T is the number of W. All of them are the same. Oh, is there any questions about the main theorem? This is our goal today.
So when T is a Q and all the W1 to the WQs are the 1?
No. Q go to infinity.
I know, I mean,
And other things are fixed.
I know, but what I want to ask to you is just assume that when all the W1 to the WQ are just a 1,
Yes.
Then
W1
isn't
to
it
W
the
T.
yeah? So then isn't it the same bound with the Friedman and Kolmos bound for the perfect hashing function?
Sorry, I do not know the bound you say. Maybe we can discuss
Yeah,
later.
okay.
And here, t is fixed. If you want t equal to 2, then things can be very different. The first step of our analysis is to transfer it from the matrix to a hypergraph. Hypergraph have the edges and the vertices. For vertices, we have n rows, and for each row, the ith row corresponds to part vi, and with each vi, it contains q points, which means we can draw something like this. This v1, v2, and this vi, and this is vn. So the number of vertices is n times q. And every column corresponds to one edge. So if the column is showing this way, we just go for this. So each column maybe looks like this. Column go to n edge, and the vertices are those vertices. So under this correspondence, an NNQ hash family is just an uniform n-pi hypergraph with little n edges and an equal part size q. Then we can write NNQ hash family into this form. How can we write T separating property? Here, T equal to n. So n separating property. How can we write it in the language of the graphs?
Right. So can I ask? I'm still like it's slow. So when you have a hypergraph, then how do I read the function? Like for instance, f1. Is it
F1, FQ? I think actually function is missing.
Function is missing?
Yeah, function is missing, and each column go to one edge.
Each column become an edge.
Yes, and the function like each function just go to one part. There are capital N functions and there are capital N parts, and each part has q vertices. For the rainbow, for the T separating property, we use what we call vertex rainbow cycle to describe it. In the present paper, rainbow cycle maybe, or the edge rainbow cycle, but here we are different. So in short, a rainbow cycle of length k, it is just a k Birch cycle, such that all the vertices are in k distinct parts. Here, each vi is one part. Or if you wanted to see the full definition, it says here. Then we can see that if we define Gn star q to be the extremal number of linear hypergraph, which is a subset of this, and forbid all lengths of rainbow cycles, then it is actually an PHF. So we will have such an equation.
And how do you give a coloring on the edges of this cyclogram?
How do I get the coloring?
So
Each part is one color. We say each part VI is one color.
So it's vertex coloring, right?
Yes, vertex coloring. So here we get vertex rainbow cycle, not edge rainbow cycle. If you wanted to see this, maybe I can give you a small example. For example, when t equals to 3, we say it do not have a 3-length rainbow cycle, then it is 3 PHF. How do we say this? For example, we choose 3 columns, which means 3 edges here. If there exists one column such that if there exists one row such that it separates these 3 columns, then things are done. Otherwise, there exists 2 columns with the same value, which means they intersect in the same vertex, right? Then we consider the second one. If things goes like this, then this is nonlinear, because linear graph, 2 edges only intersect on one vertex, so it must be goes like this. And for some reason, the third row it must go like this, and this forms a rainbow cycle of length 3. Because this vertex, and this vertex are in 3 different parts here. So
Here you do not insist A, B, C are distinct, right?
no, A, B, C can be the same, because here means V1A, and here means V2B, and here means V3C. There are 3 distinct vertices. So after knowing this, we only need to prove the extremal number is at least 2 minus 1. So our next goal is to show how do we construct such a graph with enough.
Why is the graph linear?
The graph linear means 2 edges on the intersection of 2 edges is at most 1.
Why it is linear?
Why it is linear? If it's not linear, then this we cannot get. But
so you define the graph using the original matrix?
yeah,
And
the original matrix may not be linear.
okay. And then why is there a linear in this definition?
Because if we add a linear, we can get this.
Yeah, but we want to understand why this inequality is true, so we need that. Yeah. So this, is it from this hypergraph formulation? Or?
Actually, if we want to prove this, maybe very long. So, but it just gets some very detailed analysis. So for t equal to 3, this is simple. But for higher t, we need to go through something like do induction, something like this. Okay, then we go to the next page. How do we construct this graph? Because we are supposed to construct nearly 2 square edges, so it's very natural for us to use 2 of these elements to control one edge. We define an edge in this form. Here, each slope B1, B2 to BT will be chosen later, such that those edges are rainbow cycle free. And if we define each edge like this, then themselves are linear, except maybe first if Bi equal to Bj, then non-linear, and if some Bi equal to 0, then non-linear. But for other cases, they are just linear. And here we also need FQ to be prime. Okay. So after we define this, how do we say a rainbow cycle of length k? We say we see firstly a rainbow cycle of length 3. For example, this is V1, V2, and V3, and this is E1, E2, and E3, and E1 means X1, Y1. E2 means E, X2, Y2, and E3 means E, X3, Y3. Then E1 and E2, they intersect in V2 means X1, B2 X1 plus Y1 equal to B2 X2 plus Y2. And E2 and E3 intersect in V3 means B3 X2 plus Y2 equal to B3 X3 equal to Y3. And we also have B1 X3 Y3, B1 X1 plus Y. This is how we get this functional equation here. This is for length 3, but this is for arbitrary length k. Here k is an integral from 3 to n. So after we adding up all those things, we can get the linear equation in this form. So if we choose x1, x2, x3, something like that, in a set such that no solution to this equation, then we can forbid one rainbow cycle in this form. So through this path, our problem becomes a solution-free set problem. We want to find a large enough solution-free set of many linear equations. How many linear equations shall we forbid? Is there any problem about this? Okay. We say as long as n equal to t is fixed, then we can bound the number of equations in a function of t. After we given the set of slopes R, which means B1 to Bt, we define an R permutation sequence of length k as in this form. Here Bi1 to Bik are all from R, and they are mutually distinct. Then 1U can form one linear equation in this form. We say this linear equation as Lu. So the number of the equations we want to forbid is at most the number of U, and the number of U is upper bounded by a function of t. Furthermore, all those equations they share a property such that if you add all these coefficients together, it goes to 0. Because Bi1 minus Bik plus Bi2 minus Bi1 plus Bik minus Bik minus 1 is just 0. So the equations satisfying this property we call they are invariant equations. And invariant equation means what? It has a trivial solution. If we choose x1 equal to x2 equal to xk, then this is a solution of this equation. So we say a solution is non-trivial if all of those xi are not all the same. We do not need to forbid the trivial solutions, because if all the xi, x2 to xk are the same, then after we take this into this, all the y1 to yk are the same. And all those k edges are actually the only edge. So we do not need to forbid the trivial solution. We just need to forbid the non-trivial solutions.
Solution free of L means no non-trivial solution or no trivial solution.
No non-trivial solution, right? Here I made a mistake. Solution free means no non-trivial solution. Okay. Sorry. Yes, thank you very much. Oh. Actually, our goal now is to find a good set of slopes such that there exists a large enough m. What means large enough? Means m is at least this kind of number, such that m is LU free for every k permutation sequence. As long as we can find such an m, then our graph here, it will have the size of m times q number of edges, which means at least q2 q minus all the edges. And this is exactly what we want. And until here, do we have any questions? Then next, we will show how do we find such an R. Not all R have this property, such as a large enough m can exist. Okay. first we give such an R. If R looks like this, then we say it will have marginal n. Maybe this is still too abstract. We can remove this. So what does these two blue rows saying? The first row says BT equal to little o of m. Here m is q1 minus o1. It's just a little smaller than q. So for sure we can just say it is BT equal to little q. And the second row means BT minus 1 equal to O BT, and BT minus 2 equal to O BT minus 1 until B1 equal to little O of B2. So you can imagine it like a ladder. So there are B1, B2, B3 until BT, and then it's come to M. M is almost Q. It's something like that. And after the definition, we know that the smallest one, B1, is still very large, because log B1 actually is log M 2t, 1 over 2t, right? So when M goes to infinity, B1 also goes to infinity. They are far from the constant. You can see it in this form. We will prove that if we choose R in this form, then R will give a large M.
How do you make each PI integer? Do you have a ceiling or floor or something?
Yes. But I just remove it for simplicity. The first reduction is that we need to only consider one LU instead of all LU. We need one more definition, is that we say L is C good for some fixed C from 0 to 1 if we can find a large enough L free M. And C is here. C is here to control the lower bound of M. And if we do simple calculation, we can know this one is M to 1 minus O1. And we say such M witness this C goodness of L. And this lemma shows if we have finitely many invariant equations and over finitely many unknowns, such that each equation is C good, then we can always find a common M witness all those R copies of C goodness. So as long as we can find a C such that for each LU it is C good, then we are done, because we can find an M such that it is C good for all the LU. The proof of this lemma use something like probability method, just a random shifting. And they show that there must exist a shift such that the cap of them also is large enough. And then another observation is that we have many LU, but there exists one kind of very good LU such that we can get their C good immediately, and we call such good LU convex. A convex LU just means if we separate those AI from positive and negative, if they are negative, we just store them into the other part of the equation. Then only one of those AI are positive, or only one of those AI are negative. Then we call this equation is convex. And as long as one equation is convex, then we can say directly that it is C good for some C. So after those two things, the proof goes like this way. This is a set correspond to all these LU. Permutation sequence of and we use one dot to present one LU. Then we have another set which we know these are the set of convex equations such that 3/4 good. We know that as long as one LU lies in this, then it is C good immediately. And of course, there are some intersections there. Then, how do we prove our things? Firstly, we go to the other. We will show a link lemma, which means if one L looks very like some LU here, and we say this feasible. If one L looks very like an LU here, we can always find two different equations. We denote them like L prime and L prime prime. L prime and L prime prime satisfies that as long as one of them is C good, then we can deduce that L is C prime good. Here C prime is a function of C. And we call this link lemma. And L prime and L prime prime we call the ancestors of L. Only when L is very similar as some LU here, we can have this link lemma. And then what we do is for every LU here, we find the ancestor and find the ancestor of ancestors. Something like that. It can grow as very large. And we say that after finitely many steps, those ancestors one of them must lie in the convex equation set. Actually, we can do this as t minus 2 steps. Here t is given. So after these 2 steps, we can prove our math theorem. We do not go in details. So then we can conclude our talk today. The first problem is that our main result answers the open problem of Blackburn as long as this one equal to 2. So what about any other order? For example, when order go to 3, go to 4, go to 5. In this sense, because we know when order equal to 2, we prove by linear graph. But linear graph has an upper bound of q to 2. So when n goes larger, the order goes larger, we need new ideas to do this. But fortunately, separating hypergraph may help us. So if anyone know about Brown-Alder source theorem, then maybe you are familiar with this note. FRNVE, which means the maximum number of edges in an R graph of n vertices, such that any E edges contain at least v plus 1 vertices. This is an extremal number. And Alon and Sophia, they proved this result. And by choosing n equal to 2k minus 1, actually this result gives P3 and Q for any n. Not only those n such that this equal to 2. So this means when t equal to 3, for perfect hash family, it's done. But for p equal to 4 or higher, I can only say that there are some improvements, but yes, if you are interested, we can discuss it later. And the second open problem is about when the upper bound equal to 2. Our corollary shows the C value either it reaches the theta of Q squared, or it is Q2 minus O1. So if we give W1 to WT, can we determine whether Q squared hold or Q squared minus O1 hold? Can we fully determine this? And moreover, if Q squared hold, can we determine this ratio? C value divide Q squared. There are already some results on sham-proof code, which means separating hash family with t equal to 2 and W1 equal to 1. So in this case, for the sham-proof code, they say Q squared is right, and moreover, the coefficient is determined. But as for any other types, this is still widely open. And thank you for listening. I welcome questions.
Thank you. Any questions?
So instead of using the Lucia's theorem for the invariant linear equation C2B, use a more improved bound like done by Kelley and Mecca, then can you improve your bound for quantitatively?
So
the solution free.
What is the bound you say?
I mean, there was a very huge improvement, maybe 2 years ago. So they says that the
Kelley Mecca.
Yeah, Kelley and Mecca.
Okay. I tried this, but unfortunately,
I think.
no. I cannot see how they can improve this. Okay.
Where is the Lucia's theorem was used in your proof?
Sorry. Where it was?
The Lucia's theorem.
or root out 0.
I mean, you.
The question is, where did you use that?
You use what?
RUGSA, Lucia, Imre Lucia.
Oh, sorry.
No, you're asking where you use
Yeah.
this theorem.
Which theorem?
Lucha's theorem.
Lucia.
At the
You
beginning.
mentioned it,
At the beginning.
yeah.
Yeah,
that's fine.
That
Oh.
more,
So,
more. Here.
Yeah.
Oh. Here I just write it here because Q1 minus O1 is the best solution. We cannot improve this to Q.
I see.
I write it here just to say this, but I skip it.
I was a bit confused because there was all these abstract definitions, but can you say, like, I tried to decode what you tried to prove, and then can I say something like, so your bound is like, for whenever n is smaller than, I'm confused. Whenever n is smaller than q to the 2 minus 0, 1, then for any t functions from n to q, blah blah blah. Can you say something like this, or can you express your bound in terms of some existence theorem or the some? Yeah,
Okay.
I'm a bit confused.
Look, my bound is TQ is at least Q minus 1. And PTTQ is just something like we have a matrix of T rows, and it is on FQ, and it's satisfying the property that T separating property, which means if you choose T columns, there must be one row separated.
One note that entries are all distinct.
Yes. Then we can extend the number of columns to Q to 2 minus 1.
Meaning that there exists a certain configuration like
Yeah.
this.
So is this clear?
But is it obvious to see why q square works, or
Why Q
yeah,
square
why
works?
there's no.
Do you have the upper
Yeah,
bound?
the other one. Yeah, upper bound. What about
Upper bound is Q to Q. This is the upper bound.
Is there a natural way to
yeah?
see it?
Is there like obvious reason why there is an upper bound?
This because we only have T rows and we wanted to separate T columns.
So
Then we can give this upper bound. I'm not sure what is a satisfactory answer, but from this one we know the upper bound is Q squared.
Or can you move back to your main theorem?
move
Move
the
back.
slide. Yeah.
Move back one slide. The other way.
The other way.
Okay, so they proved this PTTQ is little on Q squared.
Yes.
So is it hard to see that if you have Q squared rows, why it couldn't work?
Columns.
Columns.
Yes.
Yeah.
Well, for this part, it is just use the removal lemma.
See.
The provement of this part is from the removal lemma. But sorry, I did not find a way to say why Q square do not work.
In triangle removal or hypergraph removal lemma in there.
Sorry.
The hypergraph removal lemma or just
Yes,
triangle
hypergraph removal lemma.
Yeah, why it only works for t equals 3 and 4 cases?
What? Sorry.
Maybe we can discuss it.
Yeah. Oh, I see. So only for T is 3 or 4.
But I think that's more for the lower bound.
Yeah.
So do you have the same upper bound for all t? The little o square upper bound?
Over here.
Yeah.
This is upper bound, this is lower bound.
But this is not a literal, this is a big O. So
Yes. So actually they did more than just give a lower bound. This is the main result.
So did they prove that only for t equals 3 and 4, or
Yeah.
did they prove it for more values of t?
They prove only for t equal to 3 and
Also for the upper bound.
4. No, upper bound for t.
So they proved PTTQ is little o q squared for all t,
Yeah.
using hypergraph removal lemma.
Yeah.
I see. Any other questions? Okay, if not, let's thank the speaker. Yeah?